This is a spring reverb tank from a Fender guitar amp, and in this video we're going to take a look at the response and actually try to measure it using a function generator and oscilloscope. But first of all, what is reverb? Well, reverb is an effect which makes it seem as if the sound is being played within a large space, like a concert hall or a cathedral. And it does that by emulating the echoes and the delays that would occur within such a space. So let's take a closer look at the tank itself. So this particular tank uses 3 springs, and the springs are supported at each end by a short support wire that's housed within these little brass sleeves at each end. And also at each end are a pair of transducers. So there's an input side and an output side. And the 2 transducers actually are very similar, but they're not identical, so you can't just switch the input and output around. Let's take a closer look here. So in this case, the input transducer consists of a laminated iron core, which is C-shaped, so it's closed on one end and open on the other. And also mounted on the core is the input coil. And then within the gap of the core, where the support wires pass through, each support wire has a little magnetic bead attached to the wire. And so when the core is energized and a varying magnetic field is created within the gap of the core, then the magnetic beads will respond accordingly, and exciting the spring. Now it's interesting to note that actually the action of the spring in this case, or of the magnet, is actually torsional. So the action is rotational, and not a sort of a plucking of the string as you would have in a guitar. Now the other end, the output transducer or receiver, is very similar. The core is a slightly different design, and I guess the coil is also different and has a different impedance. But other than that, they're quite similar. At first glance, the 3 springs appear to be all the same. But if you look closely, the top spring actually has fewer turns per inch than the other 2 springs. In fact, the top spring has the fewest, the bottom spring has the most, and the one in the middle has somewhere in between. And I gather what they've done is that in the manufacturing, the springs were initially cut to different lengths. So then when mounted in the tank here, they're all stretched out to the same length, but the one that was shorter in the beginning, which in this case is the top spring, ends up with fewer turns per inch, which means it's under higher tension. So the tension in the 3 springs is all a bit different, higher at the top and lower tension in the bottom spring. And so that means that the signal will propagate at different rates through the springs. So the one under highest tension will propagate the fastest, and the one with the lowest tension will propagate the slowest. And so that's important because if there were only one spring, then the effect wouldn't be realistic. So by incorporating 3 springs with different rates of propagation, it more accurately reflects the real world. Well, in our setup here, the function generator is connected directly to the input of the amplifier. And then the signal passes through a couple of amplifier stages before it's sent out to the reverb tank. And then at the other end, the signal is picked up again and returns to the amplifier. Now, on the input side, the signal is on the order of a couple of volts, which is needed in order to energize the springs sufficiently. But at the other end, the signal is very low. It's on the order of just really a few millivolts because of the losses that occur through the spring. So then it goes back to the main board here and is amplified again. So I've got a 2-channel scope here, and the first channel is directly monitoring the input to the amp, and the second channel is looking at the output of the amplifier, which receives the signal that's returned to the amp from the reverb tank. I did try connecting directly at one point to the output of the reverb tank, but the signal is too low and it picks up a lot of stray noise. So I'm monitoring the signal at the output of the preamp. Looking at the scope, this first view gives you sort of a global perspective of what's going on. So the bottom trace in yellow is the input to the amplifier. So you can see it's a narrow pulse, and the pulse is being repeated once every second. And then the top trace in purple is the output of the reverb tank after it's sent back to the amp. In fact, if I unplug the headphone jack, you can hear it. Sort of sounds like a gunshot or a hand clap, followed by subsequent echoes. Now let's zoom in a bit further here. Let's take a closer look at the input pulse. So the input pulse is about 250 microseconds in duration, and it has a peak-to-peak amplitude of about 200 millivolts, which is well within the normal range for a guitar amp. Now let's see if we can actually measure the delay. So I'll expand the trace a little bit. So you can see that there's a train of 3 pulses coming back. So the first one is at about 22.6, 26.6, and 28.6 milliseconds. So those 3 pulses correspond to the single trip delay through the 3 different springs. And I can prove that if I touch the springs one at a time. So right now I'm touching the top spring. And you can see the first pulse disappears. Oops. And if I touch the middle spring, then that one disappears. And if I touch the bottom spring, then that one disappears. So clearly the 3 pulses are the result of the 3 propagation delays through the three springs, and the shortest delay is through the top spring, which we know from earlier has the fewest number of turns and therefore the highest tension. But it doesn't stop there. Let's look further down the road here. So there's 3 more pulses coming back here. One at about 66.8, 78.8, and 84.7 milliseconds. So those delays are actually 3 times the delays that we measured a moment ago. And that's because the first pulses are the result of the single trip delay through the reverb tank. But then at the end of the spring, a portion of the energy is picked up by the receive transducer, but a portion is also reflected back to the other end of the spring, and then reflected again towards the receive end where it's picked up. So that's why these second set of pulses come with 3 times the delay of the earlier ones. And looking further down, there's another one at about 111, 131, and 140. So those delays are 5 times the delay of the first received pulses. And you can even go beyond that. These next ones, 155, 183, it kind of gets hard to measure after that, but those ones would actually correspond to 7 times the delay. But you can also notice that the amplitude is getting less and less each time, because there's an energy lost each time the signal is reflected, and that results in the overall decay of the signal. I guess another thing to notice here is that so the input pulse that we're providing is a unipolar, positive unipolar pulse, but then the received pulses, they're not quite pulses anymore. And okay, so we'll start with these ones here. So these ones, they look sort of like negative pulses, but there's also a lot of other kind of squiggles going on there, and that's because of the finite frequency response of the tank. So that results in some ringing. So what starts off as a purely unipolar impulse kind of turns into something that looks a little bit more sinusoidal. In fact, what you really want to do is measure the envelope delay, but the easiest way to do that is just to measure to the highest point, to the peak here, which is pretty close to the peak of what would be the envelope otherwise. In addition to the impulse response that we just looked at, we can also try to measure the frequency response. But as you're going to see, it's not that easy because the reverb tank has a lot of different resonances at different frequencies. So this is a 1 kilohertz sine wave that we're feeding in right now. And okay, I'm going to step back down to 100. And we'll just do a quick sweep here. So this is the response at 100 hertz, 200, 300, 400, 5, 6, 7, 8, 9, 1,000, 1,100, 1,200, 1,300. Anyway, I think you get the idea. Basically, the response is not at all smooth, and that's due to the large number of resonances that exist within the tank. Another way that we can try to measure the frequency response is to sweep the input frequency. So right now, the signal generator is set up to output a sine wave starting at 10 hertz and increasing to 10 kilohertz over 10 seconds, and then repeating. And the scope is in FFT mode, which is basically like a poor man's spectrum analyzer. And the display is set to peak hold mode, which means that the maximum value over time will be displayed at each point. So after a few sweeps, the spectrum sort of builds up. And you can see that at the low end, it cuts off below about 100 hertz. And at the high end, it seems to roll off around 7 kilohertz. And that corresponds with data that I found on the Accutronics website. Accutronics is the manufacturer of this particular reverb tank. So about 100 hertz to 7 kilohertz is the frequency response of the tank. The other thing is that the resonances don't seem to be quite as much of an issue here. I think they're still there, which accounts for the ripple that you see in the spectrum there. But I guess because the input frequency is changing continuously, that the resonances don't have as much of a chance to occur. So that was really just a cursory look at the impulse response and the frequency response of the Spring Reverb tank. Of course, nowadays it's common to emulate that effect using digital electronics or software, and that might be something that would be fun to try sometime. But I think if you wanted to make a really good emulation of Spring Reverb, you'd need to do a lot more measurements than what I just did, and probably account for a lot of non-idealities in order to get an authentic effect. But maybe one of these days I'll try to do something like that and then make another video.